Good morning, everybody. I'm pleased to be the first to speak today in this second day of the International Conference on Electrical Systems and Automation. So I'm YAZAMI Rachid, Electrical Engineering Department, and from last year laboratory in the National School of Applied Sciences, Florida. So you are most welcome. It is a very big event for us. So the program is designed in order to attract your attention. And so I trust that we would be successful. But in looking at the participation, we are, of course, very pleased. Let me share with you that we have put a lot of patience in the program of this conference that would hopefully get us closer to you, their audience, and also to the greatest researchers and experts around the world. In different fields, of course, of renewable energy systems, power electronic systems, and control systems and automation, intelligence, and embedded systems. I will keep it short to say again, you are welcome, how much patience in the program, and how much we wish that you will enjoy this 2 days with us. Donc, to open this conference, we have, of course, 3 keynote speakers. The first we face with us today is Mr. Rachid YAZAMI. So, Mr. Rachid YAZAMI, as you know, is from Morocco, graduates of the Global Institutes of Technology, Electrochemistry, and Material Science, where he also received PhD on rapid integration components for lithium battery application, and began his career and rose to research director at CNRT in Europe, France. Mr. YAZAMI is an inventor involved in more than 140 papers for patients related to battery technology, including on safety of charge, safety of health, and safety of batteries with ultra-fast charge technologies. He also invented the graphics anode currently used in most commercial lithium-ion batteries, and filmed for Professor YAZAMI for over than 250 papers and peer-reviewed papers and book chapters on batteries and battery materials and systems. So there is a lot to say about Mr. YAZAMI. So in this context, I have the honor and pleasure to invite Mr. YAZAMI to present your famous presentation entitled Smart Batteries for Future Electro-Mobility. So thank you so much, Mr. YAZAMI, to start your presentation.
Okay, well, thank you very much for the introduction. I guess you can hear me very well, and you have the first slide of my presentation today. I'm very glad to be part of this event on the International Conference on Electrical Systems and Automation in Florida. This is the first time I'm talking to the audience of the ENSA, or the School of Applied Science in Florida. And thank you very much for the invitation, and I hope my talk will be of interest for you. As you may know, I've been involved in battery research for over 40 years. I recently, like 2 years ago, retired from the CNRS, the French National Research Center in Paris. After over, we have an echo here. Is it? Can you? Okay, there's some noise. Okay, so the title of my presentation is give you an overview about the trends in batteries, especially the batteries that are computer controlled, smart batteries for the future of electromobility. And this is the outline of my talk. I will first introduce the lithium-ion batteries, show you what are the today limitations, and what are the solutions that we are bringing to address these limitations, like the fast charging, augmented batteries, quality control, life extension, and cell balancing. I will explain everything there, and at the end I will show you something that is a bridge between science and art, and then I go to the conclusion. So batteries, lithium-ion batteries in general, that's are used now in your smartphones and laptop computers, and you had heard probably on electric vehicles and energy storage and so on. The way they are charged is actually by applying at some stage a constant current. And so this slide shows the different techniques or protocols for charging a battery. The first one is called CCCV, constant current, constant voltage. Basically, you apply a constant current, the voltage will increase to some value, and then that's when the value is reached, we apply a constant voltage, and as a result, you can see that the current, which is in red color, drops, during the application of constant voltage. And the integration of this curve gives you the ampere hours of the cell, which is what we call the capacity, the discharge capacity or the charge capacity of the cell. There's another variant of the CCCV, which is called the multi-stage constant current, which is this B here. And here, actually, we are applying a succession of constant currents, and then during each current step, the voltage will increase until it's reached a value of a limit value, and then we end by constant voltage at the end of the charge. Okay, so this is just a variant of the CCCV. And in C, we have a combination of constant current and the pulse charge. During the pulse, basically, you can see the sign here, the signal. We apply a constant current for a very short time, and then the current goes to zero. Okay, and then we have the pulse charge here in D, and then what we call the boost charging, etc. And then there is the last one, which is not constant current. Basically, we apply a signal with the currents increasing and then decreasing, and the voltage will increase until we reach a constant voltage plateau, and then the current will drop. Okay, so all this method, at least one of this method is now currently used in all the lithium-ion battery systems, either in electric vehicles like in Tesla. Tesla, they are using probably this kind of multi-stage constant current, and some other applications in mobile, cordless tools and so on. They may be using a pulse charging and so on. So all these techniques are now covering 99% of the method that are used to charge a battery. But all this method has something in common, that at least one stage we are applying a constant current, except in this one, the voltage trajectory, which actually the current is not constant. Okay. However, all these methods are unable to charge a battery in less than 1 hour. Okay, you cannot fully charge a battery, lithium-ion battery, in less than 1 hour, whatever the method you are using. Okay, and that poses a problem, because for some applications, especially in electric vehicles, you don't want to wait 1 hour to charge your battery. Whereas when you have an internal combustion car, like a normal cars with gasoline or diesel, you go to a gas station, and you fill your tank in 10 minutes. So 10 minutes should be the good time actually to fully charge a battery. And today, except with what I am going to show you, there is no technology in the market that enables us to charge a battery in 10 minutes and keep the battery in safe and not heating too much. Okay, so there have been a review actually in about 2 years ago about the fast charging. This is a paper that you can actually download and read it. And basically the conclusion of the authors of this paper is that if we want to charge a battery in less than 1 hour, using whatever the technique that I just showed, we have heat generation, you have metal plating, which is a problem during the charge of the battery. That's lithium metal is deposited on the anode side, which is based on graphite, and the material degradation because of the heat generation. And also you cannot charge 100% if you are using less than 1 hour. And also it affects the cycle life of the battery and also the safety, which means that if you are pushing the battery to the limit, the battery may catch fire and explode and so on. So it is not recommended today to fully charge a battery from 0 to 100% in less than 1 hour using the conventional methods. Okay, so I will go a little bit on this. So today, in the lithium-ion battery for the electric vehicle applications, there are several limitations which I would like to cover in this presentation. Number one is the safety. Safety is very important. We want to avoid any thermal events when we are using a battery. And unfortunately, all the time we are hearing bad news that some batteries catch fire, people are either injured, burned, or even they lose their life. In some cases, like 1 week ago in Singapore, we had a whole house caught fire because they were charging a small scooter, two-wheel, what we call in French trottinette, electric scooter like this in the house, and the battery was in bad condition, or the charger was not good. So it caught fire, and the full house has caught fire, and fortunately there was nobody injured because people had the time to run out of the house before anything happens. So this kind of thermal events happens all the time, so we have to pay much attention to the battery safety. The other limitation or the problem or issue with the lithium-ion batteries is the long time for charging. And this one today is about 1.5 hours to 8 hours, but it has to be reduced below 30 minutes. And I will show you how we address this issue. Also, the other one is the short driving range of the battery, because when you fully charge your battery in your electric car, you want to drive more than 500 kilometers or 400 kilometers, and even reach 900 kilometers every time you charge a battery. So that's another issue which is not solved yet, because internal combustion cars, if you fully charge, if you fill your tank, you can drive more than 600 kilometers. And the last but not the least is the short life of the battery. In an electric car, you need to keep the battery for 10 years. And today, probably in some cases, the life of the battery doesn't exceed 5 years. So I would like to present you the solution to all of these issues that we have been working on for the last 4 or 5 years. So number one is safety. So this kind of picture we don't want to see, like a car catching fire. Unfortunately, it happens from time to time, as I mentioned. If you Google, you put a lithium battery fire explosion, you will find have more than 1 million hits. So it's unfortunately very frequent. It can be any device that's powered by lithium battery, electric cars, cell phones, laptop computers, and scooters and everything can catch fire. So actually what the scientists and those who are working on batteries have actually assigned the thermal runaway of a battery to the presence of an internal short circuit. So if you have an internal short circuit in the battery, which means that the anode and cathode, which are separated by a separator, which is a microporous polymer, if this, for some reason, there is an electric contact between the anode and the cathode inside the battery, you have a short circuit. And that short circuit will create a current inside the cell, and owing to the Joule effect, the current will produce some heat, and then this heat will propagate, and then eventually you have a thermal runaway because the temperature in the cell is beyond some safety limits, and you have a thermal runaway and gas formations and fire and so on. So if we could detect an internal short circuit in a battery before, at the very early stage, we may be able to save lives of people and avoid, the thermal runaway and the fire of the battery. So how can we do that? Today, I can tell you there is no known technology to predict the internal short circuit in a battery. As you know, even Samsung and Tesla and other very famous companies in the world, we hear from time to time that either from Samsung, like cell phones, or for Tesla cars, catch fire. So it means that these giant companies haven't found a solution to address the safety issue of the batteries and also the early stage detection of the internal short circuits. Here we have found a solution, and I would like to very briefly cover it. So the solution consists of measuring the thermodynamics of the battery, entropy and enthalpy. It's very simple. If we can measure the open circuit voltage of a battery and how this open circuit voltage varies with the temperature of the cell, we can have entropy and enthalpy. And what we found actually in some batteries, there is a difference in the entropy data according if the battery has or doesn't have an internal short circuit. So this slide shows for the solid line here in pink color, this is the entropy profile versus enthalpy of a cell that has no internal short circuit, this one, okay? Solid line. Now, if we create a short circuit in the battery, you can see, for instance, at 3.7 volt here, the entropy value at very specific enthalpy value or voltage, which is here 3.7 volt. At 3.7 volt, you can see that the entropy value is different from the in the batteries that have an internal short circuit as compared to the battery that has no internal short circuit. So this is very, very simple and very straightforward technique. If you have a battery and you know the chemistry, you can very easily determine at which voltage you can see the difference between a battery that has an internal short circuit and not. So in this case, 3.7 volts. So basically, I will drive the voltage to 3.7 volt. I will measure entropy at that set of, the voltage. And then I can see if the entropy data falls on the solid line or departs from the solid line, as in the case here for the green one. And definitely in like a channel, what we call channel 6, we could find a large difference in entropy data at 3.7 volt between a cell that has no short circuit and the one that has short circuit. So this is a physical, based on physics of the battery, entropy and enthalpy, you know, are thermodynamics. They are relating to the state of health of the anode and the cathode. And so if there is a short circuit, we can detect it in advance and take the battery that is suspected to have an internal short circuit from the battery pack and avoid any thermal runaway. Okay. So this is our solution to this, and we are in the process actually of commercialization, a chip that will be embedded in each battery, and we can measure the entropy and the enthalpy of the battery at different voltages or different states of charge, and compare it to the entropy of the battery that has no internal short circuit. Okay, now fast charging. So for fast charging, which, as I said in the introduction, there is no technology today enabling us to fully charge a battery in less than 1 hour. Although there have been many announcements in the by some cell phone manufacturers or even electric vehicles. If they announce less than 1 hour, it means they are not giving you 100% of the state of charge. Okay, so here, when we say we charge a battery, it means that we go from 0 to 100%. Okay, that's very clear. So we are fully charging the battery, and we are doing this in less than 1 hour. So we used a technique that we call non-linear voltammetry. I think linear voltammetry, probably in the audience, people know what we are talking about. I mean, if you take a battery and you apply a voltage ramp like this at a constant slope, the dV over dt is constant. The voltage increase one way and decrease the other way linearly with time. And the response, the current that crosses the battery has generated this kind of profile, which we call a cyclic voltammogram. Okay, this is a cyclic voltammogram. Okay. Now, the linear voltammetry is not able to fully charge a battery in 1 hour. I can tell you it's not possible. What we introduce here is a non-linear voltammetry where in which the slope, the voltage versus time, is not constant. It depends on many parameters, including the current, the voltage, the time derivative of the current, the state of charge, and the state of health of the battery. So we developed a protocol that actually this function here, we can control at each time if this condition is met or not. If it is not met, we just go to current 0. So this is a profile of non-linear voltammetry. This is the voltage profile. You can see here actually we have a voltage plateau in a very short time. And there is that plateau. You see that the current is never constant. So the current is always increasing when we apply a voltage plateau, and then it decreases and so on. Okay. Now there are important parameters to the what we call NLV, nonlinear voltammetry. So this slide shows an example of to illustrate how the NLV works. So basically in NLV we have a succession of voltage plateaus like this one, and this one. And in each voltage plateau, we apply a constant voltage, and we monitor the decrease in the currents during the voltage plateau. And when the current reaches some value, okay, we go to 0. The current goes to 0. We call it a rest. And that rest takes only a few seconds. And then we apply this plateau again, and so on, until the current drops below some value that we have here. When the current drops to this value, we go to the next plateau. So we increase the plateau by a delta V here. And delta V is actually defined by the equation that I showed you before. Okay, here, this equation, this one. Okay, so we apply this equation, and that gives us the next plateau. And we repeat this plateau as often as possible until, you know, we go to the next plateau and so on. So the voltage profile here shows the during the charging of a battery at different cycles. So this charge is in 15 minutes. We go from 0 to 100% in 15 minutes. This is the first time I think you can see charging a battery in less than 30 minutes or 20 minutes. This is in 15 minutes, and we were able to apply NLV for more than 300 cycles. And you can see here that the charge profile is almost the same, whatever the number of cycles we have run between 0 to 300 cycles. Okay, so this NLV, what we found is that it applies to any type of battery chemistry, lithium-ion battery with graphite and lithium cobalt oxide, LCO, graphite and NMC, nickel manganese cobalt, and graphite lithium iron phosphate. This is the very famous cathode material. Graphite is always the anode used in lithium-ion batteries, but the cathode materials can be very different. Okay, so the different chemistries, different form factors, cylindrical, prismatic, and pouch cells, and also different capacity going from below 1 ampere hour, like here 100 milliampere hours, to more than 50 ampere hours. And the largest battery we tested had 55 ampere hours, and very soon we will be testing 63 or 64 ampere hour cells made by a Chinese company. And the other thing is that we were able to charge batteries from 1 hour, this is the maximum time we have used, to 6 minutes. And 6 minutes today is the world record for any charging method. And we are proud actually that we have achieved that record here in Singapore. And also the other thing is that we can apply NLV for charging from any initial and for any final state of charge, like from 0 to 100%, from 20 to 100%, from 10 to 90%. It depends actually on the application. In electric vehicles, most of the battery, I mean the car manufacturers, the EV manufacturer, they will recommend the driver to charge their batteries when the state of charge falls to 20%. Don't wait to go to 0%. In some other applications like drills and cordless tools, it's recommended actually to go from 10 to 90%. So case by case, we can apply the NLV to different initial states of charge and final state of charge. The very, very, very important thing is that whatever the charging time, whatever the chemistry of the batteries, we never exceeded 50 degrees C when we charge them, okay? And 50 degrees C is considered for us as the safety limits. We don't want the battery to heat up more than 50 degrees. Although some manufacturers like Samsung, they told us that we can go to 60 degrees without any problem. But we decided actually never to go to higher than 50 degrees. So now I would like to show you some examples, illustration of the fast charging of cell, lithium-ion battery cell from Samsung called the 30T cell. And this cell is commercially available. You can buy it. It's a very good cell called the high power density cell. Okay, so this is the shape of the battery. It is 21700, which means that the diameter of this cylindrical cell is 21 millimeter, and the height from here to here it's 700 millimeter, which is like 7 centimeter. Okay, so it's 7 centimeter high. Okay, so the weight is here, the capacity 3000 milliampere hours, and this is the energy density. It's 162 watt-hour per kg. So this battery is mainly high power, not high energy density, but it's very reliable and it is very used in cordless power tools. Okay, So this, I will show you briefly the profile during charging of temperature, voltage, and current. So on the left-hand side here, this curve, the red curve here shows the voltage during the charging in 60 minutes, and this is the current profile. So you can see the current is never constant, okay? And there are peaks of the current here and the others and so on. So this is a typical profile of NLV, and we were able to charge the battery here in 55 minutes, is less than 1 hour. And this is the temperature profile in red. You can see that the temperature didn't exceed 28 degrees C. So 28 is here, okay? So when the battery is kept in an environmental chamber at 25 degrees C or 24 degrees C. So this is the profile of the same cell when we charge it in 30 minutes, about 30 minutes. Okay, you can see that the voltage is almost the same as in the 1 hour. It has many plateaus. You can see the plateaus, the voltage plateaus here, and the current profile here. And the voltage is higher than 4.2 volt. It goes to almost 4.3 volt. And the temperature when we charge the battery in 30 minutes is about 30 degrees C, which is still very, very cool. Okay. Now, if we go to 20 minutes, you see it's a little bit more than 20 minutes, 22 minutes. We can see that the voltage is a little bit higher. It goes to 4.335 volt, and the current is same. You know, it's never constant, and the temperature is about 34 degrees at the end of charge. Now we go to 16 minutes. So the voltage here is close to 4.5 volt, okay, which by the way is higher than what Samsung is recommending. Samsung recommend that we should not exceed 4.2 volt, but in our case, if we use NLV, the fact that we are using higher voltage doesn't affect much the life of the battery and its safety. So in this case, the temperature goes to 40 degrees when we charge the battery in 16 minutes. And then we went to 10 minutes, about 10 minutes, maybe 11 or 10.5 minutes or something. So you can see here the voltage profile, plateaus, succession of plateaus with the plateau steps here. And when the current goes to zero, this is where the current goes to zero. We call it rest. And you can see on the right hand that the temperature during the charging in 10 minutes, it kept below 50 degrees and almost reached 50 degrees after 10 minutes of charging. Okay, the interesting thing, it's whatever the charging time in the x-axis here, from 60 minutes to 10 minutes, the capacity of the cell hasn't changed. It's always 3000 milliampere hours, okay? That's very important. We are really charging the battery 100%. That's very good news, okay? And the other thing is that this NLV technique can apply also to batteries assembled in series and in parallel. So this is just one example where we put 4 cells in series. This module is called 1P, 1 parallel, and 4S, 4 series, okay? So in this case, this is we charge it in 30 minutes. And you can see here that the voltage can go to about 17.5 volt, okay, and the current can go here to about 12 amp, okay, for in this case, okay, up to 4 amp, and we were able actually to do many cycles like this. We did 400 cycles without losing capacity of the battery module, which has 4 cells in series. The very interesting thing is that we compare the voltage of each cell, V1, V2, V4, during the charge. You can see that whatever, they are all the same profile. All the cells have exactly the same voltage profile during the NLV testing for series. And that's very, very important. If we don't see much differences between the cells, it means in this case we don't need to do so-called the cell balancing. we don't need to spend time to do the cell balancing, which is now required for when Tesla charge their battery. At the end of the charge, they have to do the cell balancing, which takes a long time, which takes another 15 minutes. Okay, now the temperature, you can see here that the temperature of the cells varies at the end of charge between 47 to 50 degrees C here, okay? So there's not much differences in the cells when we charge them. See here, the charge time is 9 minutes, but we are using only 85% of the state of charge. If we go from 10% to 95%, temperature never exceeded 50 degrees. And also there's no much difference between the cells and temperatures. So my message here is that I am announcing to you now is the end of constant current based charge. This constant current technique has been used since the inventions of the first batteries in the 19th century. The lead acid battery was the first rechargeable battery that was developed by Mr. Planté in, I think, 1858 or 59. Okay, so it is a 19th century invention. And until now, until 2021, we have been using constant current to charge batteries. So to me, what I'm announcing, the NLV puts an end to whatever constant current based charging, and we think that NLV is the solution. We can use voltage driven charging versus current driven charging, and by doing this we can fast charge the battery without overheating, and also keeping the life of the battery long and not having any thermal events. The safety also, we solve the problem. Okay, so this is the message. Now, besides fast charging, we did also another thing that is counterintuitive. I just illustrate this is what we call augmented batteries. So we have a battery at initial state of capacity is 36 ampere hours, and we charge it in 20 minutes. You can see here 20 minutes we were able to charge it to 36 ampere hours. So when we run an NLV test, one of the parameters we put in the computer is what is the capacity that we want to reach. So instead of putting 36, we put 38. And you can see actually that we were able to charge the battery in 20 minutes here, but we could increase the capacity of the cell by 5%. Okay, now we did also 39 and 40 ampere hours. So we went for 36 to 40 ampere hours. We augmented the cell capacity by 10% very successfully. And you can see here that the current profile is different, okay, in each case, all right? And even we push the limits to 45 ampere hours. So we were able to add 25% of the energy in the same cell without changing the chemistry of the cell. It's a same cell, and we could actually extract 25% more energy from that cell. So this is what we call augmented batteries. Only by changing the way we are charging the battery, we can add energy to the battery. That's okay. So this is counterintuitive, because when Samsung telling us their cell is only 3,000 milliampere hours, we have done a test today. We could extract 3,600 milliampere hours from the cell. And so we augmented the battery from Samsung by 20%, from 3,000 to 3,600. And the battery didn't heat up, and we didn't, the battery is not affected much. The capacity of the battery, cycle capacity, was not affected by the fact that we have extracted 20% more energy from the cell. So this is just to show you the voltage profile. We do this augmented battery testing. This is 30 36 ampere hours, 38, 39, 40, and 45. Okay, so the voltage, you can see that at the end of charge, the voltage here is about 4.8, which is higher than the 4.2 volt that is recommended by the cell manufacturer. But when we use NLV, we can go to higher voltages without destroying the battery. And also this is the temperature profile during the augmented battery testing. You can see 36, we are at the 36 degrees C. When we went to 38, 39, 40, you can see that at 40 ampere hours, we were about 41, 42 degrees C. And then when we went to 45, ampere hours, the temperature of the cell did not exceed 46 degrees C. So we are still in the safe side of the battery. Okay, the other application of this NLV is the quality control of batteries. This is called the stress test. And what does it mean? All batteries are different. They have many different chemistry, different engineering, different design, and so on. So all batteries are not designed for all applications. And it would be very dangerous actually to use a battery which is designed for high energy in a high power system. So the test that we are applying here is to decide whether a battery can be used for a specific application according to what the system in which the battery will be used is designed. Okay, so this stress test, basically what we do is we charge a battery, for instance, in 30 minutes, and we look at the temperature profile during the charging in 30 minutes. And if we put the limits of safety at 50 degrees C, so we have here 4 cells, A, B, C, D, and you can see that the cells A, B, and D, all these 3 cells, the temperature exceeded 50 degrees C, okay? Only one battery, which is cell C here, had the temperature below 40 degrees C. So for that charging in 30 minutes, only cell C passed the test, okay? Very important, very important. So I will not use cell A, cell B, and cell D to charge in 30 minutes using NLV. Otherwise, there is a risk of thermal runaway, okay? And by the way, the Samsung 30T cell, it's passed all the tests from 60 minutes to 10 minutes, okay? And you can see here that when we use 10 minutes, the temperature is 50 degrees. It's still below the limit. And when the charging time is 15 minutes, 20 minutes, 30 minutes, and 1 hour, you can see that the temperature profile is dropping. So we are below the limits of 50 degrees C. So this battery 30T cell can be used for many applications where the fast charging is required. And that's why we are talking now to some power tools manufacturers in America, and we are working with them to implement this technology to enable fast charging of their battery pack in 10 minutes, and they are very happy actually to work with us. Life extension, that's very important. The thing is that if we apply a voltage control technique to charge a battery, it's changed totally the story, because voltage means that we are not obliging the battery to charge at any rate, any current. So the current response of the battery is natural. I apply a voltage plateau and I leave the battery respond naturally to that increase in voltage. And by doing this, we can extend the life of the battery by very much. So this one is an illustration of what we have achieved by charging a battery below 30 minutes, and we were able to do 1,300, like 1,300 cycles without deteriorating much the capacity of the cell. And in other applications, we achieved 900 cycles, but we stopped because charging for many hundreds of cycles require lots of time. So anyway, this battery, according to the manufacturer, we cannot do more than 600, 700 cycles. This is what they told us. Now we extended the life by a factor of 2 at least, okay? And by using NLV, we can extend the life of the battery, which means that if this battery is used in an electric car, instead of last only 5 years, we can extend the life to 10 years. That's very important. Okay, so the last thing is the cell balancing. I don't want to spend too much time on it. Cell balancing is an operation that is used when we use constant currents, charging, because there is a distribution of voltages at the end of charge. All the cells are not at the same open circuit voltage. So basically what we do during the cell balancing is to bring all the voltage of the cells, all the cells at the same voltage. And that requires some charging or discharging of the cells and so on. It takes a long time before we do the cell balancing. Instead of if we use NLV, as I told you, the voltage V1, V2, V3, V4, you can see here, it's exactly the same. There is no difference in voltage, which means that we don't need to do cell balancing. And by the way, we did more than 400 cycles without cell balancing. And that saves a lot of time, saves a lot of course, money, and also extend the life of the battery. So we don't need to do cell balancing anymore. It's a part of the 20th century technology. If we apply NLV, we don't need to have cell balancing. Okay, so as I said, over 400 cycles we performed without cell balancing. That's very important. Okay, now I would like to go to the next slide, which actually goes from science, technology to art. So basically, when we do an NLV test, we end up having a very heavy, very heavy table, Excel table, a very busy Excel table with many columns, with many data. And basically, most of the data, we plot them versus time, like voltage versus time, temperature versus time, capacity versus time, etc., or we do current versus voltage or something like that. This is typical way of plotting the data. But if we take random columns and we plot randomly columns, the ones versus the other, we find something that is very funny, which I found quite artistic, and I would like to show you some examples of this. So this is this picture comes from an NLV test, okay, where we plot a Y versus X, which is not the typical one that we use, so this is one example of an art, maybe a picture or graphics derived from the NLV test. This is another one, just to illustrate, an NLV test here. Very different from what we see. This is another version of the first slide where we just changed the colors. You see it's very nice, and it's something that we didn't expect to see. This is another illustration of what we can get from NLV. This kind of profiles, another profile here. So I have like at least 200 slides like this, very different from each other. When we just plot different randomly some X's versus Y's versus X's and so on, and we can find very funny, very unique and original pictures that nobody can do unless they do NLV. Okay, this is another illustration. You see it's like a architecture or something slide and so on. So anyway, to summarize my talk, and I would like to thank you for your attention. So we lithium-ion batteries are dominating the markets of rechargeable batteries because they have very high performance, and the market is increasing by 20% every year. So this business is very, very profitable for those who make batteries and integrate them in whatever devices, including electric vehicles. For the specific application of electric vehicles, we addressed at least 4 issues. One is safety, life extension, the charging, and also the increase in energy. And also recycling. I haven't covered the recycling, but we are working also on recycling batteries. Now, the solution that we have proposed take into account the early detection of internal short circuit in a cell, and energy enhancement, like going from nominal capacity and increasing the nominal capacity by 20%. The result of this, it means that if you have a car and your manufacturer said you can do 400 kilometers, actually, if you augment the capacity by 20%, you have 480 kilometers. That the system is adding 80 kilometers to your battery pack without changing anything except the charging method. It's only the charging method. And also quality control and cell balancing and so on. So I believe personally that the NLV protocol will be the method of the protocol for charging batteries of the 21st century. It will be applied starting next year, inshallah, in some devices, commercial devices, and little by little we see it as replacing the constant current based charging method. Okay, so this is, I would acknowledge my co-workers, Professor Douglas Maskell, who is from the Nanyang Technological University, School of Computer Engineering, and Engineer Sri, also from NTU, and also Audi, my co-worker with the KVI here in Singapore. And with that, I would like to thank you very much for your attention, and I will be happy to take some questions, but I have to leave in 10 minutes from now. Thank you very much.
Thank you so much, Mr. YAZAMI. Okay, thank you so much, Mr. YAZAMI, for this wonderful presentation, which is indeed very effective and clear. You see how much lucky we are to have such personalities with us in this international conference in our school. So I would like to thank you for this contribution, very inspiring and encouraging our students, PhD students, and also our professor. So we have, can you hear me? Mr. President and Mr. YAZAMI?
Yes.
Okay. So
any questions
yes,
from the audience?
We're going to move now to
So I think this conference has been recorded, correct? You have recorded it?
Yes, the video conference was recorded.
Okay.
So you have stated or mentioned the different economic issues of fast charging. You propose a different solution which have actually the return of safety, charging time, driving range, battery service life, and so on. So you propose also the KVI solution that contain internal short circuit detection, linear or non-linear voltage for symmetry, and the ultra fast charging, which you mentioned different type of fast charging of our devices. Charge in 20 minutes, charge in 16 minutes, and charge in 10 minutes. That's very good, very interesting. You give or you gave some tests of the quality control of the battery. So this presentation was very interesting and encouraging us to know a lot of things about batteries. So just I summarize the presentation. Here is any questions, please. Oh, sorry.
Thank you very much for your nice presentation.
I have difficulty to hear, to understand the question. Could you just use the mic directly without, because I don't know if the microphone, is it inside the room, the conference room? There's an echo. There's an echo. I cannot, hear very well the question. So maybe you can either write it, or if you can use just one microphone so I can hear you better, please.
Prof. YAZAMI, do you hear me?
Ah, very good. Now I can hear you very well. Okay, go ahead. Yes.
Okay, thank you, Prof. So I'm Driss Yousfi from ENSA Oujda.
Mm-hmm.
And my question is about the profile or the charging protocol you presented in this keynote. So I think it's an issue of charging. So you have been talking about how to charge the battery. So
yes.
So I think it's a problem of designing a special charger that could control voltage in special profile. And you are applying, sometimes you are applying zero voltage.
Zero current. No, zero current, not zero voltage. Zero voltage means that I have short-circuited the battery. No, I never apply zero voltage, zero current, zero ampere.
Okay, so I'm just wondering about the peak current that appears when charging the battery. Does it affect the battery? This is my question.
Actually, yes, the peak current can be very high, okay? Yeah. But because we are applying this current, it's natural, it's not something that we are imposing to the battery. Yeah. The battery responds to an increase of voltage or applying a constant voltage by a current. So we are not the one who are imposing this current to the battery. The battery is just saying, I can take this current without any problem. Number one. Number two, this pulse, the current pulse, okay? Yeah. Where the current is decreasing, it's a very short time. It's not a very long time. So even the pulse is high in amps. The time is short. So that means that the battery, the Joule effect, where the battery should heat up, doesn't take place because of the very short time we're applying this current. Okay, so again, if I tell you I have performed more than 1,300 cycles to the same battery, okay, by charging it in very short time using NLV, that means that the battery is not destroyed, okay? It's still working. So we are the fact that we are applying a high current for a very short time, or even high voltage for a very short time, doesn't affect much doesn't degrade the battery performance. Not much.
Okay, okay. So I have just another question, please. So could we use this technique even for lead acid battery? Because it will resolve a lot of issue with PV systems.
Okay, we don't. We actually, let's say we. There are two things. I am an entrepreneur and inventor. I think in the introduction, Professor Bin Dawood said that I have more than 150 patents. I have more than 180 now. Okay, but it doesn't matter. I want to file patents. Okay, when you file a patent, basically you say I have developed a new method to charge batteries. You don't say if it is a lithium ion or something. Just NLV we can apply to any battery where we can measure the voltage and the currents, and that's it. Now in the patents you have to give some examples, and the examples we have given in the patents are all about lithium ion batteries, okay? But in the description we insisted that this technique is universal. It applies to any type of chemistry, okay? Even though we haven't tested on lead acid batteries, we did it on nickel metal hydride. It works in metal hydride, but we haven't used it on lead acid batteries. But if you read our claims, we do claim applying this method to lead acid batteries, okay? So it's not like we are not cheating. We are just saying we have proven the concept of the method to lithium ion batteries. What we don't see any problem, a priori to apply it to any other chemistry. So to answer your question, no, we haven't tested NLV on lead acid batteries so far. We haven't done it yet.
Okay, thank you very much, Prof. Thank you very much.
Thank you.
Welcome.
We have another question in the chat to you, Mr. YAZAMI. So the asker said, thank you very much. What is your opinion on LFP technology and its perspectives?
Okay. So LFP is lithium iron phosphate cathode material, and a lithium ion battery design. Okay, so just to summarize very quickly, when you build a battery, you can decide if the battery will be high energy or high power type, okay, with the same chemistry. So same chemistry, you can make a battery of high energy, in which case you densify the electrodes and the electrode thickness is higher, or you can design with the same materials a high power density battery with a porosity, higher porosity in the electrodes, and also thinner electrodes. Okay, all right. Now, if you take lithium iron phosphate LFP battery and you design the highest energy density possible using LFP, okay, in this case you never exceed, say, 120 or 130 watt hours every kilogram. 130, let's keep the number, 130 watt hours every kilogram. Okay. Now, the best battery using oxide, like nickel, manganese, and cobalt, NMC battery, the best battery has more than 260 watt hour per kilogram, which means that an LFP battery designed for high energy and NMC based battery for high energy the one based on NMC has 2 times more energy density, which means that every kilo of the battery will give you more than 2 times or about 2 times the energy of LFP. So LFP, when you think about high energy density, is not competing with NMC. Definitely, NMC will win. By the way, in your cell phone, all batteries in cell phone are not using LFP. They are not using phosphate at all, because energy density is so low. It means instead of using your cell phone for 1 hour continuously, you will use it only for 30 minutes. Okay. Now, for other applications where actually the energy density is not the most important, like energy storage systems. Energy storage system is a system that's where we store energy from solar, wind, hydroelectricity, or geothermal energy, and so on. We store it in a system that is not moving. It's a stationary. In this case, lithium LFP-based batteries have a better advantage than NMC, because the power density of these batteries is much higher. Okay, we can charge them very fast, which means that if you have a lot of wind, suddenly you have a lot of wind and you have a lot of electrical energy, and you need to store that's a lot of energy in very short time, then LFP is much better. Okay. Now, when I said we broke the world record of charging a lithium-ion battery in 6 minutes, 6 minutes was achieved with LFP battery. Only LFP battery enable us to charge the battery in 6 minutes without exceeding 50 degrees C. Okay. Now, the interesting thing that for electric cars, historically, a major company that maybe you know in Morocco, this Chinese company called BYD. They are in Shenzhen in China. BYD started to commercialize electric vehicles using LFP in China. And they apply it mostly to taxi drivers. And electric taxi, if you land in Shenzhen or Shanghai, if you take a taxi at the airport, the electric taxi will have LFP-based battery. Okay, because this battery is safer, cheaper, and so on. Okay, and it can allow us to charge quite fast. Now, what happened is that BYD found that their customers, they need more driving range. Like LFP will allow you to do only 300 kilometers every time you charge, but you need 400 kilometers for some reason, or 500 kilometers, in which case LFP cannot make it. So BYD started to shift from LFP to NMC batteries. Okay. Now, what will be changing the story is the fast charging. So if I am able to fast charge LFP battery in 6 minutes, there is no more problem. Which means that if I have 300 kilometers range, I can drive 300 kilometers, stop at a charging station, go to have a coffee. 6 minutes later, my battery is fully charged, and I can drive another 300 kilometers. So 300 kilometers is enough for driving between Casablanca and Marrakesh, and maybe from Casablanca to Fez without recharging your battery. But if you want to go from Tangier to Agadir, you have to stop maybe 2 times to charge your battery in 6 minutes or 10 minutes and so on. So just to tell you, because of the development of the fast charging technologies based on NLV, I think LFP batteries will become #1 choice in electric vehicles. And it will replace little by little the NMC-based batteries. That's my personal opinion, and you will see in 5 years if I'm right or I'm wrong. Okay, so LFP has still a huge, potential to be used in electric vehicle in the future.
Thank you very much, Rachid, Mr. YAZAMI. Actually, my question, you responded very well, because my question was around the mobility and cars using these batteries, and also one of the solutions we're developing at my company it's a mobile charging unit. We choose LFP batteries for it, and yeah, you confirm that it was a wise choice, either in the density of the battery and also the power and the
range, charging range.
Yeah, the range. Thank you. But we've seen that you're working on something that will be revolutionary for cars, that will be reducing the time of charging by 2. Is it something already mature? Can we find it on the market? If yes, where, and if no, when? So this is my second question.
Okay. Well, I mean, we have partners. We have, unfortunately, not in Morocco. I have been trying to introduce this technology in Morocco, but Morocco is like this. They are not ready. Okay. But it's not final decision. We can still do something in Morocco. So now, because to answer your question, I think in 2022, you will see this technology implemented in some devices. And I think the first device will be like a power tools, like a drill or whatever tools that you are using without cordless, okay? Because the market is huge, and also the amount of batteries is not that much. The pack is less than 100 watt hours or something. It's not very high. So this is where we see personally with the collaboration with a giant company in America that does these devices, that they are willing actually to introduce this technology, commercialize it in 2022. So I'm very confident. Now for electric vehicles, I think it will take another maybe 2-3 years until 2024, because as you know, battery pack is maybe maybe 50, 60, 80, 100 kilowatt hours, okay? So the amount of energy is much higher, and we have to control the charging of electric car using NLV. We haven't, designed yet a charger for electric vehicles, and we are working on it with the company in Europe. I wish we could do it with your company in Morocco, but we are still open to do it if you want. We can, together develop the charger and see how we together implement the NLV in Morocco. I was having a dream, and unfortunately the dream will not be fulfilled. That's the first country in the world that can announce that we can charge a battery in 10 minutes will be Morocco. But no, it will not be Morocco, unfortunately.
Okay, just for your information, we're based in France.
Okay, you are based in France. Well, anyway, I mean, again, I mean, if you have a plan to develop this technology and bring it to Morocco, we can talk together and see what we can do. I'm very open. No problem.
Okay, I'll send you a message. Thank you very much.
Thank you very much.
Thank you, Mr. YAZAMI. I'm sorry to interrupt you. We have more 2 questions. So please.
No. Sorry, I have to go. I have to go because I have my driver.
I understand you have a very tight agenda. So
yes. So please ask people to send me a question by email, and I will respond. But I have to leave. I'm sorry. My time is finished.
Thank you for joining us.
Yeah, no problem. Welcome. Thank you very much. I'm sorry.
I appreciate that. It's very kind of you to be with us in this conference. And for another time, we are sorry for the delay. So I promise you in the second edition of our conference, we're not going to be late. Okay. So
okay. All right.
We wish you.
All right. No problem.
Next time.
We are used to it in Morocco. It's not a problem.
Okay.
Thank you very much.
See you later.
Bye bye.